98%. Just let that number sink in for a second. 98% of all international internet, data, and telephone traffic relies entirely on a hidden, completely invisible infrastructure. Every time you send an email, stream a movie, or make a global financial transaction, you are almost certainly relying on this incredibly vast, unseen network.
So, that really begs the question, doesn't it? How does the internet actually cross the ocean? We usually think of our data just sort of bouncing off satellites in space, but the physical reality is way more grounded. How do terabits of our most critical information manage to traverse the darkest, highest pressure, most hostile environments on Earth without just breaking apart?
Welcome to The Explainer. Today, we're taking a literal deep dive into the physical backbone of the World Wide Web. We're going to unpack the absolutely stunning deep-sea engineering, the highly advanced optical physics, and the massive maritime logistics that keep our modern world continuously connected.
Here is our dive plan for today. We'll start with the invisible global backbone, dissect the anatomy of an undersea cable, figure out how to amplify a light signal over those insane distances, check out the cable ships and installation process, look at the reality of deep-sea maintenance, and finally explore what these cables do beyond just the internet.
All right, part 1, the invisible global backbone and mapping the web.
Let's just take a look at the sheer, staggering scale of this underwater network, because this spiderweb is massive. Active cable routes span the Atlantic, the Pacific, wrapping all around our coastlines. These are the physical lifelines of the global economy, bridging continents in a fraction of a second and carrying everything from cloud services to military communications. And the whole system is built with extremely high reliability and redundant paths, meaning if one line goes down, the world doesn't just stop. But getting that line down to the ocean floor in the first place, that means engineers have to solve the immense problem of deep-sea pressure and the constant threat of water intrusion. Which brings us to part 2, anatomy of an undersea cable and surviving those depths. So how do we build one of these? Building from the inside out. The core features these incredibly thin optical fibers, surrounded by, of all things, petroleum jelly, which instantly blocks any water from traveling down the line. Then we wrap that in a copper or aluminum tube, add a layer of polycarbonate, and then a dedicated aluminum water barrier. For immense physical strength against that crushing depth, stranded steel wires are layered on, wrapped in mylar tape, and finally the whole thing is encased in a super tough polyethylene sheath. It's basically a high-tech fortress built to protect a few tiny strands of glass. Now, with all that crazy armor, you're probably picturing something massive, right? Well, actually, deep ocean telecommunication cables are surprisingly tiny. They're typically only 17 to 20 millimeters in diameter. That is roughly the size of a standard garden hose or a beer bottle cap. To put that into perspective, compare it to a submarine oil or gas pipe, which can reach 900 millimeters in diameter. The sheer density of engineering packed into these tiny telecom cables is simply mind-blowing. But depending on where the cable is actually laid, that armor varies drastically. While the deepest, quietest parts of the ocean can use that unarmored, lightweight garden hose-sized cable, the shallower areas closer to shore, that's the danger zone. They require heavily armored variants, ranging from light wire armor all the way up to double armor. These heavily protected cables can reach up to 50 millimeters in diameter just to survive dropping anchors and harsh, rocky seabeds. But hey, protecting the physical glass is really only half the battle. Our next major engineering hurdle is figuring out how to keep the actual light pulses, the data itself, from degrading as they travel over thousands and thousands of miles of glass.
Okay, part 3, amplifying the light signal and overcoming that huge distance.
Enter an absolute game-changer in telecommunications history, the EDFA, or erbium-doped fiber amplifier. Before this tech came along, systems used complex electro-optic regenerating repeaters, which created a massive bottleneck. The EDFA completely revolutionized the industry because it's transparent. It amplifies the light signals directly without needing to convert them into electronic signals and back again. And most importantly, it works across a wide spectrum of colors. This enabled something called DWDM, or dense wavelength division multiplexing, meaning a single amplifier can boost multiple channels of light simultaneously on a single fiber. It completely removed the electronic bottleneck and led to an absolute explosion in data capacity. And you know what's really cool? Because the EDFA simplified the underwater equipment so much, it allowed engineers to move all the highly complex receiver and transmitter functions completely out of the water.
All that sensitive, intricate terminal equipment was safely relocated to shore landings. This didn't just save an incredible amount of money, it drastically increased the reliability of the entire system. Today, engineers are pushing those boundaries even further to increase the distance between these repeaters. Newer techniques like distributed Raman amplification, or DRA, and remote optically pumped amplifiers, ROPA, are used in synergy with traditional EDFAs. These advanced schemes enhance the optical signal-to-noise ratio, keeping the light signal crystal clear while letting us span even wider stretches of the ocean floor without needing as many physical repeaters. So we've got the ultra-protected cable and the laser tech to push the data. Now we have to marvel at the massive maritime logistics required to actually execute these installations.
Which brings us to part 4, cable ships and installation, or basically, how we lay the web.
Think about the logistics here. Inside the hull of these massive, purpose-built Reliance-class cable ships, you've got these gigantic spools holding thousands of miles of cable. Highly trained and experienced crews use precisely controlled machinery, like linear cable engines, to perfectly manage the cable's slack and hold back tension as the ship is navigating the high seas. Just to give you a sense of the sheer powerhouse specs we're talking about, a Reliance-class ship is 140 meters in length, with an endurance of over 60 days at sea. It can carry more than 5,500 metric tons of cable in a single trip. They are fully capable of operating in heavy weather and come equipped with remote-operated vehicles, ROVs, and massive sea plows to literally bury the cables safely into the seabed near the shore. And look, laying this cable is absolutely not just chucking a line off the back of a boat. It requires intense desktop studies and continuous 3D bathymetry tracking. The ship uses software to ensure the cable pays out at the exact right speed and tension, so it lays perfectly flat on the seabed. If there's an underwater mountain or a trench, the engineers must navigate it perfectly, otherwise a suspended cable under tension is eventually just going to snap. Part 5. Deep sea maintenance, and a bit of a reality check. Yeah, so here is the harsh narrative twist. Despite all this space-age optical tech and meticulous installation, the physical underwater world remains a brutal, totally unpredictable place. These tiny cables face constant hazards. Remember how the unarmored telecom cable is only 17 to 20 millimeters wide? Well, a commercial fishing trawl dragging along the bottom can range from 5,000 to 50,000 millimeters wide. Combined with dropping ship anchors, unpredictable seismic activity, and massive underwater landslides, it's amazing they survive it all. And when one is damaged, the effects are immediate. Data has to instantly reroute, which often causes much slower internet speeds for entire regions. So when a break happens, an incredibly suspenseful timeline kicks off. First, engineers have to remotely locate the exact spot of the break in the pitch-black deep sea. A repair vessel is immediately dispatched. Once on site, they literally grapple the broken cable from the ocean floor and pull it all the way up, miles to the surface. Skilled crews then painstakingly splice the glass fibers back together, test the connection, and carefully lay it back down on the seabed. It is a massive undertaking that typically takes about a full week once the ship actually arrives on the grounds. Finally, Part 6, beyond just the internet, a scientific network. I want to broaden the scope a bit here, because the truth is this huge infrastructure does so much more than just let us stream videos or process financial transactions. Scientists have realized that this web can be utilized for incredible scientific applications. They're using these cable networks to transmit critical, real-time data from remote sensors back to their laboratories. This means our internet cables are doubling as real-time climate monitors, feeding global weather prediction systems, tracking shifting ocean currents, and even detecting seismic activity to warn us of tsunamis. We've effectively turned the internet's backbone into a giant planetary monitoring system. How cool is that? There's a quote that I think perfectly summarizes the beauty of this dual purpose. These cables not only keep people connected, but also advance our understanding of Earth itself. It's an economic lifeline and an environmental tool, operating silently in the deep, completely out of sight. So I'm going to leave you with this thought. The next time you send a quick message or load a web page, will you picture that actual beam of light shooting through a tiny tube sitting at the bottom of the ocean thousands of miles away? It's a remarkable physical reality behind our seamless, everyday connectivity. Thanks for joining me on this explainer, and keep questioning how the world around you really works.